Okay, welcome back. Our next speaker is Pietro Ortoleva from Princeton.
Hello. Hi. Thank you for, let me thank the organizer. This was fun, super nice, awesome, everything. View, food, everything. And talks. So today I want to talk about a paper that it's part of a long series of papers that I started working on when I was in grad school with this chap, Mark Dean. And then we kept on working on these sort of related topics, and then a bunch of people joined along the way, Colin Kammerer, Jonathan Chapman, and Eric Snowberg. And it's a sequence of projects in which what we try to do is understand relation, in the sense empirical relations between behaviors. And in this specific project, what we try to study is the relation between fairly basic notions in behavioral economics, which are the willingness to accept, the willingness to pay, and loss aversion. So let me try to explain. All right, so the basic idea and the starting point is related to what David was talking about this morning, and is the relationship between the willingness to pay, accept, and willingness to pay. So just to recap what David was talking about this morning, suppose that I have an object, a wonderful pointer. It's actually a nicer pointer, I know. So this wonderful pointer, you may be interested in computing what is your willingness to pay. You don't have it. I show it to you and say, hey guys, how much would you pay for this? All right, I record it. In a separate group of people, I give them a pointer. I say, hey, it's yours to keep. But hold on, before you go home, would you sell it back? How much money would you want to sell it back to me? And I'm going to call it the willingness to accept. Now, according to standard theory, bearing income effects, which we know don't matter, so trust me on this, they should be one and the same, right? Because that should be the value of the object. But of course, as you probably know, Nobel Prize were awarded for the observation that they're not the same. And in fact, the willingness to accept is bigger than the willingness to pay, which is called, again, the endowment effect. And this is kind of a big deal because it means that we don't have a unique notion of value that we use when we make purchases or sale. Right? It doesn't mean, the fundamental idea of, 19th century economics is that we are human machines, we attribute value, we operate on value, right? That human machine notion doesn't work, at least in this evidence, because we don't buy and sell just based on that value. All right, so big deal. Now the beauty of this is that when people discovered this, they also had the story ready. And the story is the prospect theory story. The story is, you know why I have a higher willingness to accept than a willingness to pay? Because I am loss averse. The intuition is that losing is painful. Or to cite Kahneman-Tversky, losses loom larger than gains. Now, if I think about selling as foregoing an object, as losing an object, this loss is painful, and I don't want to incur it. And therefore, to be compensated to sell an object, I want more money than I'd be willing to pay if I didn't have that object. And that's the fundamental explanation of the endowment effect in the literature. This is the leading explanation. To the point that, somewhat annoyingly, the literature sometimes misuses the word loss aversion to denote the endowment effect, even though these are separate notions. Instead, loss aversion as a notion has a history of its own. It was introduced by Kahneman-Tversky in the uber-famous prospect theory paper, and has to do with an overweighted losses in mixed gambles, or essentially a loss of risk aversion around zero. Now, while I was speaking, Christoph was shaking his head. Now I'm curious to see. You had, oh, okay, sorry. I thought I had made a wrong historical citation. Christoph knows history better than I do, so I thought, all right. Okay, good. Another observation before we move forward. So this is the leading story. But even with this story, you may agree with me that the WTA and WTP should be related with each other, right? So sure, they might not be the same, But somebody who's willing to pay a lot probably also wants a lot to buy, and vice versa. All right. What I'm going to do today is to present an empirical paper in which I'm going to present the outcome of 3 incentivized surveys on 4,000 participants in a representative sample. So this is a very large-scale study. In fact, these are 3 large-scale studies, fairly well paid, a bunch of people. And in these surveys, we measure the WTA and the WTP for lottery tickets. I'll explain why lottery tickets is essential for whatever I'm going to say later. We're going to measure loss aversion, and we're going to measure loss aversion in a bunch of ways. And we're going to measure a bunch of other stuff that I will reveal as we go along to keep you interested. Moreover, I'm going to do some stuff. We're going to measure each of the things a bunch of times because one of my co-authors is a very good econometrician, and so he gave us sophisticated ways to measure, to use measurement error. And so, you know, I'm going to add some bells and whistles. We're going to create a panel data, so we're going to measure these things over time. We're going to test for stability. So as we go along, I'll give you some features about this. But the key thing we're going to derive from here is that I'm going to use this data to document 3 facts. Fact number 1, the endowment effect and loss aversion are independent. So the key feature is this. Prospect theory says people have the endowment effect because they are loss averse. Our data says no. There is no empirical relation between loss aversion and endowment effect. These 2 things do not relate with each other. So the loss aversion explanation of the endowment effect is really not supported. 2, the WTA and the WTP are actually independent. This is going to sound funny. How can they be independent? I'll try to tell you that it's not funny. But they're independent traits, even though we still get the endowment effect. That is, WTA is on average higher than WTP, but they are not correlated traits. This despite the fact that, just one second. Oh, yeah. Hey, let me just throw the perfect. Now, you may look at this and say, all right, but maybe this is all noise. And the answer is no. Because what I'm going to show you is that the WTA and WTP are not related with each other, but they are related very strongly with a lot of other stuff. And also they're stable over time. So we have panel data, so we can test stability over time. So we have stable, these things are stable, they're just not related with each other. So what I'm trying to tell you here is the following, that there is a lot of structure. It's not that this stuff moves randomly. If the world was random, it would be a very sad world for economists because there would be no models to write, and as a theorist, I would be very, unhappy. But luckily for us, the model is not random. There is a ton of structure, but unfortunately, this structure, or actually, fortunately for young people, this structure is not the one we thought we had. So we have more theories to write. Yay! Okay, Christoph. Very good. So I'm going to show you this. No. So I'm not going to claim that in general WTA and WTP are not related. My wife is allergic to fish. She's going to have a very low WTA and WTP for sushi. I'm not, and I love it. I'm going to have a very high one. And of course, these things are going to be correlated. But so I'm not arguing they're completely independent, but I'm going to argue that in the world of lotteries, they're independent, that this is going to be important for point 3. For point 1 is also going to be important that I use lotteries because I need to make sure I'm evaluating everything on money. I'll elaborate on this in a moment.
So about fact number 1, so you are rejecting the prospect theory with that? Really?
No, I'm just saying, or at the very least, I'm saying, look, prospect theory says that one is explained by the other, but they're not related empirically. So, insofar as I can test it, it's really rejected.
Okay.
Okay, so let's see. A couple of questions before I move forward. How can this be new? Right? Prospect theory, Nobel Prizes galore. How can we, nobody tested this thing. I don't know, but nobody did. It turns out that if the only papers about the relationship between the endowment effect and loss aversions, well, one was written by me and Mark. And another one is a working paper that I think recently got published, but it does things in a very different way. So for some reason, people never bothered to test the relationship between the endowment effect and loss aversion. I don't know why, but people never bothered. We did, and it turns out that, in fact, if you look at these two papers, there is a relationship which is fairly mild. And this is very different data. It's computed in the lab in a very different way. So, as we go along, if you have time, I'll try to explain why we get different stuff. Also, you may also wonder, didn't people ever test the relationship between WTA and WTP? This also sounds not a crazy thing, no? You get the data, just plot this thing out. Well, it's subtle. People compare the averages. They looked at whether this one was bigger than the other one. To test the correlation, you need to have within subject, right? You need to have both per subject. Most experiments don't. The experiments that do never bothered. We bothered. So we looked at the old data, and insofar as we tried, for the majority of experiments, they're also unrelated. Then you have some that are very negative related, some that are very positive, but like we're talking about old experiments with like 7 subjects, this kind of thing, so I don't know what might be. But on average in the data, especially if you pull all the data together, they are unrelated. So I don't think it's a special thing of our data set. It's just that people never bothered. All right. Good. If everybody's with me, let me give you a theoretical primer as to why prospect theory is predicting that they are one and the same. So as you remember, and I'm really echoing and building on what David said earlier, prospect theory says that utility varies in relation to a reference point, which is fixed. But in relation to this reference point, losses loom larger than gains according to our parameter lambda. So a typical functional form, this is a special case, but a very common special case, is that the utility for gains is a concave function, the utility for losses is the reflection, but it's not exactly the reflection, it's a reflection weighted by a parameter lambda, which is called loss aversion. Now, how do you get the endowment effect out of this? Well, if you encode the act of selling as a loss, now loss aversion generates an endowment effect. Why? Because when I own this pointer and I sell it, it's as if I'm losing it, then I don't want to lose it, so I don't want to sell it. You got to compensate me for this utility of losing. Now here is a little bit more subtle, because what I'm doing is that I'm buying and selling a lottery, and now there are many ways to do it. There are 2 big ways. One is the Kazuhiro way. Another one is what's called third-generation prospect theory. What I'm about to say doesn't matter. You can do it in either way. Now detail, and the literature is huge on these things, and people fought on a lot of details. Luckily for us, these details don't matter for what I'm about to say. In any of these formulations, the endowment effect should be related to loss aversion, and in any of these formulations, when there is no loss aversion, there should be no endowment effect, and essentially one is driving the other. And let me actually compute it, just for simplicity. I'm going to just do it in the simplest way with linear utility and loss aversion. Let me just do the algebra. Suppose I have a lottery which is half 10, half 0, and I have this simple utility. What's the willingness to pay for this lottery? Well, it's the amount such that you're indifferent between buying the lottery or not. What's the utility of buying the lottery? If you win, you get tens minus the price. But if you don't win, you get just minus the price, which is a loss, which means that if you do the algebra, the willingness to pay is 10 divided by 1 plus lambda. Now, what's the willingness to accept? Here I'm using third-generation prospect theory. Again, trust me, it's the same with Kazuhiro. This is saying if I'm have a lottery and I sell it, then it's as if I'm issuing it. So if I have a lottery and I sell it for WTA, if the lottery paid 10, I get the WTA, but I lose 10. If the lottery pays 0, I get the WTA and lose nothing. So then this is the calculation, and this is a typo. There should be no lambda here. But then you do the algebra and you get this, and then you see that the ratio is exactly equal to lambda. So you see that the endowment effect, which is typically encoded as the ratio, is just the loss aversion, and there is no endowment effect if there is no loss aversion. Now this is super simple because I put no risk aversion. I just wanted to make it easy, but you get the gist. Yeah.
Sorry to bother again.
Bother. Let's keep it
So
chatty.
yeah, this makes sense. But when you say it doesn't matter what generation of prospect theory, but what the endowment is or what the reference point is does matter. Namely, that you need that is to be stable. So if I start asking questions and start thinking about selling, then already my reference point becomes the money I'm getting. But in another way, I'm asking it, then it's about not having it.
No.
So there is some stability across
No.
these
Very
things.
good. Very good. Yes.
And so
Sorry.
I thought that the Kursegraving story was, even though they pin it down with rational expectations, that if my mind just wanders around, then my endowment effect also wanders around. Because it's like mentally, this is a
Mentally, I'm already thinking of selling.
Yeah,
Absolutely.
I know it's
All
far.
of this is absolutely
Yeah.
true. But what I mean to say is that the specific form in which you encode this, the endowment, you don't have an endowment effect without loss aversion. And loss aversion, right? However you want to encode it.
Yeah, I'm saying, but it can reverse. Like what's selling and what's buying is a matter
Or
of framing.
if I enter into the
Yes.
frame of selling a
Yes.
absolutely. But here, my data is going to be really plain vanilla endowment effect kind of experiments. So fair, in fancier experiments, you have to worry. We are as plain vanilla as you can get. So, all right. With this primer, let me tell you our data. So our data is
Pietro,
the,
quick question. All this will be also if you use probability weighting, more the thing on probability weighting rather on the lambda?
I mean, if you do probability weighting, if you start making asymmetric probability weighting, then it really depends on how you encode it. Because now you start having 25 moving parts. But if you encode it in the natural way, then it would get exactly the same thing. So most people write the endowment effect lotteries exactly with the goal to say that if you have no loss aversion, you should have no endowment effect. Because people really, but I think it's a feature, not a bug. They claim, I know why we have the endowment effect. It's because we're loss averse. Right? So this is what they're trying to highlight with the theory. Okay, our data. These are 3 separate surveys run between 2015 and 2020 in various iterations, all run by YouGov. This is a representative sample of the US population. We have 4,000 people, and about 1,466 have been tested 6 months later. So we have a panel for a bunch, and I'm going to use this panel feature as we go along. As I said, we have representative samples. YouGov is considered widely to be the most representative of representative samples outside of governmental ones. And in my estimation, I'm going to use weights. If you know what these are, that's standard norm. If you don't, trust me, it doesn't matter. Also, everything I say doesn't depend on this. In this thing, we measure WTA and WTP, 4 lottery tickets for each subject. Everything is incentivized, so we pay. The order between the elicitation between WTA and WTP is randomized. The order doesn't matter. Trust me, we've been kosher. All of this, all the appropriate tests have been done. In fact, they are not run close to each other. These are fairly long surveys, and we always take care of having them appear far away from each other. Moreover, each of them is computed for 2 different lotteries. So each person gives us 2 WTAs and 2 WTPs. Okay, and I'm going to use this as we go along. The way we measure it is using a multiple price list. That is, I'm going to give you the option, and then I'm going to ask you a bunch of increasing values and ask you where you want to switch. We have a multiple price list with 4 single switching, through which subjects go through a very extensive training. We have a lot of comprehension tests and so on, so we are fairly confident in the quality of this data. All right, how do we measure loss aversion? Now this becomes subtle because there are a lot of ways of measuring loss aversions. And we try to err on the side of caution, and we measure them in 3 ways. First way, some of my co-authors' favorite way, they call it dose. This is a sequence of binary choices that are designed to estimate a parametric model of loss aversion, and these are designed so that to maximize the Bayesian information in these estimates. You know, we can spend hours about that. They have a paper about that, which is great. You should read it. But the key point here is that we use a sequence of binary choices to estimate parameters. Another way, which is maybe my favorite way, is instead we're going to measure the certain equivalence of a lottery with only gains, lottery with only losses, and lottery with equal gains and losses. And if I look at the way risk attitudes operates here, as opposed to these two, this is a measure of loss aversion. And third, what I can do is that I can measure a lottery equivalent of 0, in which I have a lottery with using lotteries with gains and losses. These are all 3 methodologies that have been used. Again, not knowing which ones is better, we tried all 3. Now, before I move forward, you may ask, why are we doing the WTPA and WTP for lotteries? Why don't we do it for mugs? The famous example from Kahneman Tversky is mugs. Mugs are awesome. They're great for teaching. Let's use that. Well, we couldn't. And we couldn't for essentially a few reasons. We picked lotteries for a few reasons. First one, traditional. The endowment effect for lotteries is one of the original examples of the endowment effect. So if you go back to, the original ones, it's about lotteries. So, and it's widely documented. A lot of people claim it's more robust than the one for mugs. So we did that. But there's a more important reason. Using lotteries is crucial to test the relation with loss aversion. Let me explain why. If you're careful and you look at prospect theory, especially the way prospect theory is used, prospect theory allows for the parameter of loss aversion to be dimension dependent. I may be very loss averse towards mugs and not at all loss averse towards money. I may be very loss averse towards, I don't know, my grandmother's recipes, which I'm very much loss averse about, but not particularly loss averse about whatever, disposable stuff. Now, instead, if I want to compare loss aversion, I want to test prospect theory, I want to make sure that I'm focusing on the same dimension. If I use loss aversion, if we measure loss aversion for monetary gambles, and therefore I should compute the endowment effect for monetary objects, therefore for monetary gambles as well. That's the only safe way of properly rejecting the prospect theory. Because otherwise you may say, oh, but you are using different dimensions, and I'm assuming I can allow for the loss aversion parameters to be different in the 2 dimensions. And there's a third reason, which is one of the reasons why the endowment effect for lotteries is very popular, which is that I can endow you with a lottery ticket without giving it to you physically. I cannot endow you with a lottery without giving you I cannot endow you with a mug without giving you the mug. But I can endow you with a ticket, which is an object that pays, and it's an abstract object, so I can endow it to you in a remote setting. Christoph. Hold on.
Money itself has no hedonic, so one could argue against it, saying that, that one could say that, yeah, this is all true and absolutely makes sense, but money per se is A, fungible, B, has no direct hedonic
Sure,
attribute.
I mean, I would disagree
so then I would say
sharply,
that, okay,
but
so,
that's fine.
So basically the argument is that if something has no direct hedonic attributes, then you can't really link, based on the data, loss aversion to the endowment effect.
I don't understand why.
No, I mean, this goes back to the issue. No, but so I'm just trying to say that in this context, it seems that what's really at stake is whether we can talk about loss aversion on money.
But loss aversion was defined for money, right? I mean, if I look
the
at
Mark story, was, I mean, it's a translation between, I understand.
whether I can talk about the endowment effect for lotteries, I can, and I do, and there is data that predates the marks. And then loss aversion was defined on money. No? Am I wrong here? If I'm missing something?
I will ask it later, but there's all this discussion about whether I'm endowed to the single dollar, $1 bill that I'm paying with, or am I endowed to a mug that I own, even though you have an identical mug, but it's my mug.
Very good. But
So, yeah.
if that was true, I shouldn't observe an endowment effect for lottery tickets,
Correct.
which I do instead.
Okay.
So that's fair. I agree. So you would say maybe there's no endowment effect for lottery tickets, but that can be good. Other observation, you may ask, why do we measure it twice? Because what we're going to do is that I'm going to talk about correlation using a technique that two of my co-authors on separate papers developed, and it's called ORIV, Obligatory Related Instrumental Variables, which is a way to study correlation using instrumental variables that reduces measurement error. So if anything, you should treat whatever I show you as an overestimated correlation as opposed to underestimate. We're using fancy econometrics well beyond my head. I mean, let me be honest, I understand a quarter of this. But it's the appropriate method. Yeah, good bit. Yeah, but here there's only one dimension, which is money. There's no mugs.
So then what was your argument about different lambdas in different dimensions?
Sorry. If we had the mugs, we would have to worry about how we do dimension by dimension lambda i's. But we don't have mugs. We only have one dimension, which is money, so we don't have to worry. Good.
Sorry, I didn't
Okay.
understand.
No,
Good.
we were on the same page. Good. Okay. All right, so let me tell you the results. Before I tell you the results, basic facts. What the WTA? The WTA is 0.9 of the expected value of a lottery, relatively well-behaved stuff. Remember, I measured the WTA twice because I have two lottery tickets. Turns out they're fairly highly correlated. They shouldn't be perfectly correlated because these are not the same lottery ticket, but they're fairly highly correlated. WTPs are a little bit lower on average, still fairly reasonable, highly correlated too. About the endowment effect, depending on the data set, remember I have three separate surveys between 67 and 62% have one strictly higher than the other. Between 9 and 16 have them equal, the remainder have the opposite. Absolutely in line with typical surveys, especially with a little bit of noise. So, you know, we are absolutely in line. The average size of the endowment effect is 0.2% of the expected value of the lottery. Sorry, not 0.2%, it's 20% of the expected value of the lottery, so fairly high. Fairly standard numbers in line with lab data. In fact, we were surprised how much in line with lab data they are. Yeah.
I don't know this literature. How are the surveys implemented? You probably incentivize them more than just asking them what would you pay for this lottery.
So what we do is that we say,
Do you sell them the lotteries?
yeah, so the way it works is this. Suppose I'm doing the WTP, okay? I say, hey, here's a lottery, okay? With probability half it pays $50, with probability half it pays 0. Now, what you're gonna do is that I'm gonna offer you a list of monetary amounts, and then you're gonna tell me for each of these numbers whether you want the monetary amount or the lottery. So I'm gonna start from 0, it's gonna proceed to 50 in steps. So for 0, you probably prefer the lottery than 0. But for 50, you probably prefer 50 than the lottery. And then at some point, you're gonna switch from one to the other. This procedure is called the multiple price list. And it's uber standard methodology. Then suppose you wanna switch at, I don't know, at a certain line. At the end of the experiment, I'm gonna randomly pick a line here, see what you chose, and if in that line you chose the money, I give you the money. If on that line you chose the lottery, I give you the lottery. And if I give you the lottery, what does it mean? That I'm gonna play the lottery, I'm gonna flip a coin, and then if... Does it make sense? So one of our goals here was to try to be the least innovative possible. So we really tried, I don't know if we succeeded not to be innovative, not, you know, to replicate the standard method, but we were really trying not to be creative. Okay. Fact 1. The endowment effect and loss aversion are unrelated. Let me illustrate. I like to show stuff with graphs. So the loss aversion, we measure it in 3 different ways, using this parametric estimation, using the 2 certainty equivalents, 3 certainty equivalents, or using just 1 lottery equivalent of 0 versus a lottery with gains and losses. So let me just explain the last one, which I think is what I'm about to show you. Suppose that I ask you, do you want 0, or do you want a lottery pays half 10, half x? Sorry, half minus 10, half hex. And I ask, what is the x that makes you indifferent? If x is equal to 10, it means that you're indifferent between 0 and half 10, half minus 10, which means that you're loss neutral. If x is bigger than 10, it means that you need a higher price to play this thing, which means that you're loss averse, and how much bigger than 10 this is a measure of loss aversion, which is a non-parametric measure, but very direct. This is actually my favorite measure. Another measure is that I can do other forms of certainty equivalence, but these are all...
Right. And it's different from risk aversion?
Very good. What's the difference?
Sounds like what they learned as risk aversion.
No, but it is. But this is so mathematically speaking, loss aversion is risk aversion around 0. So a lot of people debate, but this is what it is. So it's not. Yeah. Yeah.
So relative to other findings, which one is? So is it true that the endowment effect you find is smaller than sort of an average endowment effect, but the loss aversion you found is not? Or
No,
it's not true?
In absolute numbers, it's not entirely obvious how to compute. The fraction of endowment effect we observe is fairly in line, and the amount, I think, is not that different from typical experiments with lotteries. It's very different from the old Mux
Yeah, because
experiment.
lambda equal to 2, which is huge.
Yeah, but I think most people don't think that lambda is equal to 2 these days. In data, that's really not supported. So, if you look at modern experiments, various ones, you don't go to 2. Okay. So let me illustrate the fact that unrelated with a graph. Here I'm plotting what I just told Elios. This is the lottery equivalent. What am I plotting? Oh yeah, this is the endowment effect. And this is the lottery equivalent, this 0 indifferent to half, minus 10 half x. And here I'm plotting what are these numbers. And these are like, I'm cheating a little bit. These are not exactly 4,000 data points, because this we measured only for 2,000 people, and they're jiggled a little so that you can see them better. But as you can see, there's no relationship. And in fact, if you do a non-parametric estimation, really general, you see that this thing is flat. Prospect theory says it should be like this. It's really not like this. There's a lot of people at 0, so you might wonder about, no, this look more because of the jiggling. In fact, the mass is, the super big mass is here. So we have to redo this graph because we have to enlarge the circle. But yes. In fact, let me do slightly more careful econometrics. What I can do is that I can run regressions, and using my 3 different measures of loss aversion, and different measures of endowment effect. It could be the difference, the ratio, the square root of the ratio, which is what you get with some funky formulations. I can use loss aversion. I can also estimate a parameter of risk aversion. I can control for it. If you do some version of Kosegi-Rabin, you will get that the endowment effect should be exactly lambda to the power of 2 over alpha or 1 over alpha, depending on which version you use. We tried them all. We didn't know. We just, throw it. Stata does it for you. I mean, I do nothing. But my co-authors know how to use Stata that says how to do it. And look. No, 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 no. Not related. Never. Here, you may wonder, oh, how about, you eliminate, people that have too low numbers, too high numbers. No. It doesn't come up. We tried to massage the data. It doesn't pop up. So it's not related. So the take-home message from the
Just a quick thing.
Yeah.
Is there any separate measure of like attention in the survey, like how much attention you're paying, and see if you restrict that sample of the correlation changes?
Very good. So I don't have the graphs here. So what happens is the following. So we have measures of IQ. So if you look, and this is something we discussed in the paper, if you look at the super top percentile of the group, so these are in the top 5% of people, and you look at young people, this correlation comes back at barely significant. It is.
Or if you try to restrict to a sample that looks more like the lab samples of really smart kids in in X.
So if you
school,
got normal lab sample, not top 5%, but you go like top 50% of IQ, then this is not there. And we have a lot of data here, so we can look at response time. We can rule out people with the shortest response time. We couldn't bring it back up. So
Got it.
that's,
Thanks.
that's why we were convinced. And notice that we're stuck in, we're learning multiple regressions. I'm not controlling for my, so, I'm stuck in the deck against me, right? Because because I'm running all of these regressions and I'm running all of these subsamples, something gotta become significant. We didn't get it, so it's also true that we have 4,000 people, so, it's also harder to get spurious significance. Okay. Good. So there's no support for the endowment effect in prospect theory because what we're claiming is that these are independent traits. The second observation is that WTA and WTP, in fact, are unrelated to each other. And this is the second bit. This is the graph of WTA and WTP in our data. As you can see, there's a bunch of WTA. Oh, I forgot. This is WTA. No, sorry. This is WTP and this is WTA. I forgot to add the names. As you can see, the bulk of people is over here. There's a lot of people around here, which is not surprising. But as you can see in the cloud, there is no relationship. According to standard theory, these two measures should be one and the same. This is Econ 101. They're not one and the same. According to, once you allow them to get different, you should start getting stuff in this quadrant, and indeed most stuff in this is in this quadrant. But I'm telling you is that they're unrelated. Again, you may follow up on what Leo was saying. Maybe they're more related if I start becoming pickier and pickier. Here we did a ton of subgroups. We could not get any subgroup in which they're correlated, except, again, top 5% of IQ, young people, college educated. That's what we got. Yeah, so this is actually, here what I'm doing is that I'm just chopping extreme values. This is, again, a non-parametric fit. It's really not there. And again, I can show it to you. This
Pietro,
is
so loss aversion will ask, prospect theory will predict that you will have a linear line above the 45 degree?
No, so prospect theory depends on how you encode it. It allows for different types of correlation, but to get that they are independent using prospect theory, you need that the parameter of risk aversion and the parameter of loss aversion are perfectly going against each other, compensating. So you can get it, but it becomes super funny.
No, that's not what my question. The standard prospect theory.
Yeah.
What will be the line that will be predicted? What will be the shape?
No, if you allow for heterogeneity of both lambda and alpha, then it could be a cloud. It doesn't need to be. Yeah. It doesn't need to be the line.
Yes.
It could be a cloud. But the point is that for them to be independent, these two parameters must have a distribution in the population that exactly compensate each other, which is at the very least implausible. So first of all, it's ruling out some forms of prospect theory, and it's also very implausible for others. But potentially, sure. But we use the previous part to go against to test the loss aversion part of prospect theory. Now, and this is just to show that this thing that they're not related is for every study. If you look at averages, if you do ORIF correlation, while at the same time, the measures of WTA and WTP individually with each other, so not across, but within WTA and WTP, are strongly related. Okay, so now you may look at this and say, dude, fine, but let me give you an explanation of everything. What you get is crap. It's just a bunch of noise. You measure random numbers, and you're telling me the random numbers are not correlated, so what am I learning? Okay, let me argue that these are not random numbers. Observation 1. We use an instrumental variable trick to reduce measurement error, so that's already taken care of some. But you may say, what is this trick? Who knows? I don't know. Let me give you easier explanations. Well, second observation, WTA, the different measures of WTAs are correlated with each other, and the different measures of WTPs are correlated with each other. You say, okay, yeah, but maybe too similar. Let me give you another argument. Remember here we have panel data for almost 1,500 people. These are measured 6 months apart. So what I can do is that I can test whether these measures are stable. Incidentally, that's a whole paper by itself. So we have a separate paper about this, because to our knowledge, there's no papers about this, about stability. Now let me give you as a benchmark what is a measure of stability out of 6 months. The ORIF correlation for basic risk aversion questions in 6-month period is 0.3. Okay, and this is the highest intertemporal correlation we have. Sorry, this is not the highest, it's one of the highest. The highest we have is actually the one for WTA. So WTA, our measure of WTA is correlated over time, 0.36. WTP is correlated over time, 0.35. The endowment effect is correlated over time, 0.3. What I'm saying is that our measures are, insofar as there is stability, as stable as anything in this data. They're just unrelated with each other. And also, if you're curious, you may say, but there's something special in your population. No. My co-authors have a separate paper, which is beautiful, in which we measure the stability of preferences for the entire Caltech student body. And they find that risk aversion is correlated out to 6 months, again, 0.35. So this seems to be a fairly reasonable benchmark for stability over time, and our measures hit. So we claim these are pretty stable stuff. But more importantly, what I want to show you is that WTA and WTP are actually related to other things. Now, what other things do we have? So we've seen that WTA and WTP are not related to each other. The endowment effect is not related to loss aversion. But you may ask, maybe they are related to other features of risk preferences, because, hold on, these are WTAs and WTPs of lottery tickets. So your risk aversion got to matter in some way. Well, what do we have? We have certain equivalent of a bunch of lotteries, gains, losses, mix. We have certain equivalents for earn. And then we have lottery equivalents of fixed amount of monies and other lotteries. And you may say, how do these compare? And let me show you this table. And I'm gonna go slowly here because there's something I want to highlight. So here, I've divided my measures in measures that are called fixed lotteries. These are my fixed lottery. These are fixed lottery objects. What does it mean? This is a multiple price list in which there is a lottery, and I'm looking for their certainty equivalents. And here I have objects in which I have a variable lottery. I have either a fixed amount of money or another lottery, and I vary the lottery in the multiple price list. So this is a lottery equivalent. These are certainty equivalents. This is WTA and this is WTP. And this is the table of ORIF correlations. And what do we see here? Look, WTA is really related to risk aversion about bets on an earn, 0.66. This is super strong relation. Remember, WTA is related with itself, 0.7. And this measure is related with itself. We have 2.7. They are related across 0.66. They're really the same thing. Is this surprising? Not really. This is WTA for a lottery ticket. You see, it's not all noise. But hold on. let's look at this guy. How does it relate with the WTP? Let's see. Oh, not at all. And indeed, WTI and WTP are not related. It looks like WTP is not related to risk aversion. How can it be? That sounds nuts. All right, let's move forward. We have another way of measuring risk aversion for gains, slightly different wording. We're really trying to cover our bases. Same. Mixed lotteries, this. Lotteries with only losses, still related, not very strong. But now we get into funky territory. How about I look at the lotteries with variable, in which I vary the lottery with a fixed amount of money? Now I'm measuring lottery equivalents. Oh, WTA unrelated. And with two lotteries related, but you know, much less strong. On the other hand, look at these variables. They're very strongly related with each other. And now look at WTP. Now this guy is related with the variable lottery types. In fact, if you take these measures and you run a principal component analysis, what do you get? Of course, you're going to get two components. One that is these fellas all together, and one that is these fellas all together. Principal components are just ways to summarize correlation tables, right? That's a natural summary. So what are we seeing here? That indeed WTAs and WTPs are related to risk preferences, but with different features of risk preferences. And that's because my earn measure and my fixed money measure are not related with each other, which is incidentally well known in psychology and forgotten in economics, that risk aversion really varies depending on how to measure it. Well, it turns out that WTA and WTP are related to different features of risk aversion. WTA with the certainty equivalent, WTP with the lottery equivalent. Why? Well, turns out, not very surprising. Why? Well, here's a story. Okay, no, let me just summarize so that we agree. WTA and WTP are not related to each other, but each of them is strongly related to a different aspect of risk aversion. So in general, risk preferences have two clusters. One, certainty equivalence plus WTA. The other one is lottery equivalence of WTP. The fact that there are two clusters, these two clusters, is not entirely surprising. The fact that WTA and WTP entered this way is new. And now let me try to convince you of why it's not crazy. And you can refer to a paper by Charlie Spranger in 2017, not 1917, in 2017, that made the following observations, which is not his observation, but he tested it empirically. If you look at multiple price lists, the fixed element in the price list may act as a reference point. So when you have a certainty equivalent, your sure amount, your sure lottery of which you're looking at computing the equivalent is your reference point. And that is just like, well, the lottery is a reference point, but then it's just like the WTA, where the lottery is a reference point. If I do a lottery equivalent, the fixed amount is the sure amount, which is acting as a reference point, but then it's just like the WTP, and indeed is related to the WTP. So in a way, this structure makes all the sense in the world. All right. So let's take stock and let's go back to theories. What did we find? We found that WTA and WTP are independent. They're unrelated to loss aversion, but related to different features of risk preferences. What theories are going to go? Standard Econ 101, gone and forgotten, in the sense that Standard Econ 101 says that they should be, WTA and WTP should be equal. I'm telling you, not only they're not equal, they're not even empirically correlated. Prospect theory, that was a good contender. Awesome idea. Here it doesn't work. Not saying it doesn't work in general, but with this data, no. Other models, well, the first one I got to put is our own, the one Dudi presented this morning. told us today, and that model can explain it. But of course, this is not the only model that can explain it. Models of incomplete preferences can explain this. Models of salience can explain this. So there are models that are compatible with this evidence. And I'm sure other smarter models, maybe one of you will write, will explain this evidence. But, you know, our point here is not really to tell you which is the new model. We do it in another paper. But our point here is to, you know, to sort of take stock and start ruling stuff out. So just to conclude, in this paper we run 3 large-scale incentivized surveys on representative samples, in part of which we have a panel. And we document that the endowment effect is not related to loss of earth. The WTI and WTP here are not related. And that the data, though, has a ton of structure because WTI and WTP are related to different feature of risk preferences. This has theoretical implications. First of all, prospect theory is not doing great here, but other models are actually compatible with this. And again, my view, I have a fairly precise view about this. I see, I'm in the minority of the profession here, but I see the interaction between theory and data as a dynamic. And so I think that sometimes, you know, data should test theory, but also provide data points that new theory should fit. And so what we're hoping to do here is to provide new data points that new theory should fit. And you know, hopefully it's going to be it will be replicated, and hopefully new theories will fit. And a few caveats, just to conclude. Again, I'm really not claiming the WTI and WTP are not related to each other, because in general, of course, they might be. I'm saying that in this world of lotteries, they're not. It would be nice to test this outside. We haven't done it. It would be great to test it for, I don't know, mugs, cars, sushis, all open for future research. Of course, each of the models I've added have further implications. These further implications we cannot test in our data sets, but it would be nice to test those and see whether any of those survive. And I think I'm out of time. Yeah?